Hello everyone. My name is Dr. Aradhna Sahu, Associate Professor, Computer Science and Engineering Department from Shri Santosh Rungta Group of Institution, Rungta College of Engineering and Technology, Bhilai, Chhattisgarh. Welcome to today's lecture on the understanding wavelet based image compression. So, let's start the session. As the coming era of digitized image information, it is critical to produce high compression performance while minimizing the amount of image data so the data can be stored effectively. The image compression is essential for reducing storage and transmission requirement. So, compression is one of the indispensable techniques to solve this problem. Wavelets offer a powerful technique for achieving efficient image compression. In this lecture, we will delve into the fundamental of wavelets and then we will learn in the next lecture how they are applied to compression images using Python codes. Let's take a short recap for basics of image compression. The image compression reduces redundancy while preserving important information. It is categorized into two categories. The first is lossless compression. It retains all the information, while lossy compression, it sacrifices some details for higher compression. The word wavelet means small waves. There are variety of wavelets available which are selected according to the application. The image processing based on the continuous or a discrete image transformation are classic techniques. The images transformed are widely used in image filtering, data description, etc. Considering that the Haar and Morlet functions are the simplest wavelet, these forms are used in many methods of discrete image transforms and processing. The wavelets transformations are widely used in many research areas and its advantages over conventional Fourier transforms as it takes less time and individual wavelets function are localized in the space, but the Fourier transform cannot. Wavelets are often used in lossy compression due to their ability to capture both high frequency and low frequency component effectively. The wavelet algorithm contains transformation process, quantization process and lossy entropy coding. The wavelets are functions which allows data analysis of signals or images according to scales or resolutions, and it provide a powerful and remarkably flexible sets of the tools for handling fundamental problems in the science and engineering such as signal compression, image denoising, image enhancement and image recognition. So, basically it is a mathematical function applied in digital image processing and compression. Its main aim is to improve the image quality, and wavelets can divide the signals into time and frequency components. So, our first question is that what is need of wavelet transform in image processing? The answer is using wavelet transform, the image can be decomposed at different levels of the resolution as wavelet decomposition has varying window size and can also be processed from low resolution to high resolution as wavelet transformation is localized within time and frequency domains. So, wavelet transformation has following properties. The first is wavelets are mathematical function that can be scaled and shifted. Second, they provide a way to analyze signal and images at multiple scales. It has two main types. First, CWT, it stands continuous wave transform, and second is DWT means discrete wavelet transforms. DWT is the most suitable for digital data due to its discrete nature. There are several techniques can be used to compress the image, which are DCT, discrete cosine transform, and wavelet algorithm transform. The DCT works by separating the images into parts of different frequencies. During the step quantization, where the part of the compression usually occurs, the less important of frequencies are discarded. Hence, the use of the term of lossy. Then only the important frequencies are used to retrieve the image compression process. As a result, the reconstruct image contains some distortion, but these level of distortion can be adjusted during the compression stage. There is some loss of quality in the reconstructed image. It is clearly recognizable even though almost 80% of the DCT coefficient was discarded. The images contain large amount of information that requires large transmission bandwidths, much storage space and long transmission times. Therefore, it is crucial to compress the image by storing only the essential information needed to reconstruct the image. An image can be thought of as a matrix of pixels or intensity values. In order to compress the image, redundancy must be exploited. For example, area where there is a little or no change between pixel values. Therefore, the large redundancy occur in the images which having large area of uniform color, and conversely, images that have frequent and large changes in the color will be less redundant and harder to compress. In general, there are three essential steps in a wavelet transform image compression system: transformation, quantization and entropy encoding. Figure 1 depicts the encoding and decoding process in which the reverse stages are performed to compose a decoder. The dequantization is only the different part in the decoding process, and it followed by the inverse transformation in order to approximate the original images. In order to compress the images, the wavelet analysis can be used to divide the information of an image into approximation and detailed subsignals. The approximation subsignal shows the general trend to pixel value, and three detailed subsignals shows the horizontal, vertical and diagonal details or changes in the image. If these details are very small, then can be set to 0 without significantly changing the image. The value below the details are considered small enough to be set to 0 is known as threshold. The greater the number of 0, the greater the compression that can be achieved. The amount of information retained by an image after compression and decompression is known as energy retained, and this is the proportional to the sum of the square of pixel value. If the energy retained is 100%, then the compression is known as lossless and the image can be reconstructed exactly. This requires when the threshold value is set to 0, meaning that the details has not been changed. If any value are changed, then energy will be lost, and this is known as lossy compression. Ideally, during the compression, the number of zeros and the energy retention will be as high as possible. However, as more zeros are obtained, more energy is lost. So, a balance between the two needs to be found. Wavelet transformation involves the following steps. So, we can understand the step-by-step method for image compression transformation using wavelet algorithm in figure 2. The first step is that the original image is embedded into the system. Then the system will transform image into grayscale image to minimize the storage size in the disk. The grayscale image is go to the wavelet transformation, either first, second and third level of the decomposition. The purpose of this transformation is to separate information into sub-signals. Then the system is quantized the image. The result is a wavelet compression image where the compressed image size is reduced, but the quality of image is quite similar to original image. The purpose in transformation stage is to convert the image into a transformed domain in correlation, and entropy can be lower and the energy can be concentrated in a small part of transformed image. The quantization stage results in loss of data because it reduces the number of bits of the transform coefficients. The coefficients not make significant contribution to the total energy or visual appearance of the image are represented with a small number of bits or discarded, while the coefficient in the opposite case are quantized in a finer fashion. It is such the operations to reduce the visual redundancy of the input image. The entropy is at the end of the whole encoding process. It assigns the fewest bit code words to the most frequently occurring output values and the most bit code words to the unlikely outputs. This reduces the coding redundancy and thus reduces the size of the resulting bit stream. The main goal of this system is to maintain the quality of image after compression process using wavelet algorithm. The image quality is one of those concepts that is greater than the sum of its part, and normally the goals of image compression is to produce compressed image of the highest quality. The brief comparison of wavelet compression with some other common compression algorithms is shown in figure 3. We can see the impact of wavelet transformation in the figure 3. It indicates that the quality of original image and compressed image are similar, and it is the best overall trade-off between image quality and load image for the image compression. When we zoom out in the original image and compressed image, the purpose of zoom in these images is to compare the quality image into larger between pixel by pixel. From figure 3, it clearer represents these images are with no perceptible distortion even through it compressed with level 3 of the decomposition compression. There is no image data are lost during the higher compression. It can be concluded that when images used to achieve high compression, the wavelets can causes images to appear smooth with a wavy appearance, sometimes described as looking similar to grains of rice. Because wavelet operates on the entire image at once, they avoid the blockiness associated with JPEG methodology. It shows that comparison between size of original image and compressed image. From previous, the quality of original image are same without degrading the any image pixel of it, and there are no information loss in this image compression. Even though the quality images are similar, it reduces the size of image so that it can be transmitted efficiently. Let's understand the wavelet transform algorithm for image compression. So, it is a process that involves transforming an image using wavelet transformation and then quantization and coding the transformed coefficient to reduce the image's file size while preserving the image quality. The complete steps of wavelet compression along with the simplified diagram number 5 to illustrate this process. The step 1, image processing. In this step, we will load the input image that you want to compress. Convert the image into the grayscale. If it is in color, ensure the image dimension there are in the power of 2 by cropping or resizing if necessary. The second step is wavelet transform. Apply a two-dimensional discrete wavelet transform to the pre-processed image. The 2D DWT decomposes the image into different frequency subbands including approximation, low frequency and detail high frequency coefficients. The decomposition is typically performed iteratively, creating multiple levels of the details. Now we proceed the third step, that is quantization. Quantize the wavelet coefficient in each subband. Quantization involves mapping the real value coefficient to a finite set of values. The quantization step size determines the trade-off between image quality and compression ratio. A smaller step size preserves more detail but requires more bits for encoding. Fourth step is entropy encoding. Some entropy encoding techniques such as Huffman coding or arithmetic coding to encode the quantized coefficient efficiently. These techniques assign shorter codecs to more frequently occurring values, reducing the overall bit rate. The step 5 is bit stream generation. It combines the encoded coefficients and other necessary information such as the image dimension, quantization, parameters and wavelet transformation details into the compressed bit stream. The sixth step is compression ratio. These steps calculate the compression ratio, which is the ratio of the original image size to the compressed image size. Step 7 is decompression. To decompress the image, reverse the process. It involves extract the image dimension, quantization parameters and wavelet transformation details from the compressed bit stream, perform entropy encoding to obtain the quantized coefficients. Then apply an inverse wavelet transformation to reconstruct the compressed image from the quantized coefficient. The inverse quantize the coefficient to obtain the real value wavelet coefficients. The step 8 is post processing. If necessary, perform any additional post processing steps such as color conversion or contrast adjustment on the decompressed image. And step 9 is display the decompressed image or save it as a file in a suitable file format, for example JPEG, PNG file formats. Now we are discussing the types of wavelet transformation. The wavelet transformation is the decomposition of a signal to the frequency components. It can be continuous or a discrete. Hence, it can be classified as CWT, stands continuous wavelet transform. The CWT is a tool that gives complete signals. It does these through translating and scaling the wavelet parameter to vary continuously. On the other hand, a discrete wavelet is used to decompose the signal into sets DWT. The discrete wavelet transformation is a computerized technique to compute vast wavelet transformation of a signal. Now, we look at the properties of these transforms, and from the properties we will derive our conclusion. So, first is CWT. The CWT involves convolving a continuous wavelet functions with the signals. The wavelet function is scaled and translated to analyze different frequencies and time intervals. A well-known wavelet used in the CWT is Morlet wavelet, which resembles a complex sinusoidal. Some application area of CWT is biomedical signal analysis. In this field, like EEG and ECG and the medical imaging, the CWT is applied to analyze the detect abnormal patterns or events in biological signals. The second property is vibration analysis. In mechanical and structural engineering, CWT is used to analyze vibrations in machineries, buildings and bridges. Next is environmental monitoring. This is applied to analyze the data from sensor monitoring environmental parameters such as air qualities, water levels and weather conditions. The next property is machine condition monitoring. In industrial setting, CWT is used to monitor the health of machines and equipment by analyzing vibration and acoustic signal. It can detect anomalies and predict potential failures. The properties of CWT are: these transforms is redundant, undecimated transform. It means that it generates a huge amount of coefficient. It is not computationally efficient since it is use a huge amount of coefficient. These coefficients occupy a lots of RAM, thus hindering and execution speed. This is shift variant. You can shift the signal around before calculating the transform and the resulting energy will still be same. The CWT cannot be implemented with filter bank. It is a drawback. ICWT is not much accurate and has less stable numerical computation. Now, we will list out the properties of DWT. The DWT breaks down a signal into different frequency components using a set of discrete wavelet functions. It's a more computationally efficient method compared to the continuous transform. The signal is divided into approximation and details coefficients, which represent different scales and resolutions of the original signal. It is used in many areas like: first is image compression, the second is signal denoising. DWT can effectively remove noise from signals, making it valuable in various fields like telecommunications, biomedicals and geographics. The third feature is feature extraction. It can help extract relevant features from signal or data in the various applications like pattern recognition, image analysis and audio processing. The DWT can identify important features that represent and underlying the characteristics of data. The fourth is time series analysis. It is also used for analyzing the time series data in the field of finance, economics, and environmental monitoring. It can help identify trends, patterns, anomalies at different scales within a time series data set. The fifth is audio compression. Similar to image compression, the DWT is used in audio compression algorithms like MP3 to efficiently encode the audio signals by capturing the relevant frequency components and discarding the less important ones. DWT has two forms. One is non-decimated, which generates more coefficient, and the other is undecimated, which generates fewer coefficient. DWT is more computationally efficient because it generates fewer coefficients. The decimated DWT is not shift variant as it does downsample, while non-decimated DWT is shift variant as it does not use downsample. IDWT is the more accurate and less stable numerical operation with precision. Finally, based on CWT and DWT, decimated and undecimated property can be concluded the following points. First, if the application is to obtain the sparsest possible signal represent for compression, denoising or signal transmission, the DWT is preferred. The second, if the application requires a shift variant transform and perfect reconstruction, non-decimated DWT is preferred. If the inverse transform is not required, then CWT is used. If the application requires an orthogonal transform, DWT with orthogonal wavelet filter is the obvious choice. If our primary goal is a detailed time frequency analysis or precise localization of signal transient, the CWT is a clear choice. For example, discontinuity detection, frequency break, etc. For other applications such as denoising, compression, feature extraction, studying statistical properties of wavelet coefficient, etc., the DWT is obvious choice. Let us compare the performance of wavelet compression with some other common compression algorithm. We are doing first with wavelet versus JPEG. Wavelet compression can offer better compression quality and preserve more details in images compared to JPEG at similar compression ratio. The JPEG uses a DCT, while wavelets are better in handling edges and fine details. The second comparison is for wavelet versus MPEG. The wavelet can provide better compression video efficiency, especially for certain types of video with complex scenes or fast motions. The DWT has been used in video codec. The third comparison is with LZW, Lempel-Ziv-Welch and Wavelet used in GIF and PNG file formats. So, LZW and Wavelet are lossless compression algorithm used for next text and images. They are generally better suited for lossless compression, while wavelets are primarily used for lossy compression. Wavelets based lossless compression method exists but may not always outperform LZW or Wavelet. The fourth compression is wavelet versus MP3, MPEG-1 audio player 3 and ACC advanced audio coding. It has been explored for audio compression. in the form of wavelet packet transform, but MP3 and AAC are still more commonly used for audio compression. These formats are optimized for perceptual audio compression, while wavelets may be different trade-offs in terms of audio quality versus compression ratio. The fifth compression is wavelet versus H.264 and H.265 high efficiency video coding. These video codecs use a combination of techniques including DCT, motion compensation and entropy encoding. They are widely adopted and provide excellent compression efficiency. While wavelets have been used in video codecs, they may not consistently outperform H.264 and H.265 in terms of compression ratio and quality. In the summary, the performance of wavelet compression compared to other algorithm depends on the specific use case and requirements. The wavelets are advantageous when you need to preserve fine details and edges in images or when dealing with the certain types of data. However, for some applications like audio and widely used video compression, other algorithms like MP3, AAC, H.264 and H.265 are more suitable. In the summary, the wavelet comparison is a versatile and powerful technique that finds application in a wide range of fields. It strikes a balance between efficient data compression and data quality, making it indispensable for tasks that involve data storage, transmission and analysis. Its multi-resolution capabilities and scalabilities ensures that it remains a key technology in the realm of data compression and signal processing. Thank you for joining today's lecture on the understanding wavelet based compression and looking forward to seeing you in the next video lecture or whenever you need support. Have a great day. Goodbye.